So this is section 10.2 in the textbook. And what you see in front of you are my notes that I wrote when I was reading through the textbook. And I like this the way it is here because I think it explains kind of what you're doing in a t-test pretty well. So I'm just going to kind of walk you through that. But before I move into that, I want you to keep in mind that the reason that we do a t-test is we want to see if there's a difference between two groups. So the whole reason we're doing this is to determine if there's a difference between the groups, and we're going to call that difference D. So then, as we look down this example here, this is example 10.2 out of the textbook, and we're comparing drink calories at Starbucks before there was an ordinance that said they had to post the calories, and after, when they said that they had to post the calories. So here we have the list of calories that people purchased. You know, they just kept track of what people purchased and then they put it in here. So basically we have two means. We have this mean here, 142.95 and 140.85. And we want to determine if there is a difference between those two numbers. So I mean, of course we can look at those numbers and say, well, 142.95, that's almost 143. Is that, it seems kind of different than 140.85, but you know, they're pretty close. So what we want to do is determine if there is significant enough difference between those two groups that we can actually say, yes, absolutely, there's a difference in calorie consumption. So we do that through this thing called a t-test. And so first thing we're going to do is talk about the hypothesis. So you have to understand that we are hypothesizing about the UD difference. So we're hypothesizing about the difference, and so the null hypothesis is going to be that the difference is either equal to 0 or less than 0, because remember that the original understanding is that there is no difference between before and after the ordinance, and so that's why the difference here, and you got to remember that this is the difference, is less than 0 or equal to 0. Always the null hypothesis has the equal sign in it. The alternative to that is that it is greater than 0. So we say that so that's our hypothesis. So then I wrote out here what exactly is happening in this t-test. So here's our customers right here, 1, 2, 3, up to 40. And then before, this is the number of calories, you know, for customer 1. And then after for customer 1, and then before for customer 1 or 2, and after or whatever. So this is a matched pair comparison. So we add up this total number of calories down here, and we take the average of each of these groups. And then over here we've got this column D, and that's the column that tells us the difference. It's a lot like calculating the standard deviation. Here we have the difference between 141 and 142 and 137 and 140, etc. We add that down, we get 84, and then we have to divide by n to get 2.1, and that is the average difference, so D bar right there. So we take each of our differences and subtract off D bar, and we square it, and then that is, we're going to sum that down, and this number here is a little bit like loosely related to variance. We got to do a couple more things to it, but it's sort of like variance. You know how variance is the squared difference between the mean and the observation number? Well, so it's kind of the same thing, a little different, but same basic idea. So then we go on down here, we calculate step 4. Using the D bar from step 3 above, we have to calculate the sum of those differences right here, and we're going to divide it by n minus 1. So we just take that number down, and we divide it by n minus 1, we get this 66.50. So this number here is really our variance. Remember I told you this was the variance? Well, it's kind of the variance, but we still had to divide it by n minus 1, so we're on our way. Then we bring this number down here, we take the square root of it like this, and we get 8.15. Now this is very similar to the standard deviation in the z calculation. So we're going to take that and we're going to put it into our t formula. Now this formula here, this is just the formula that we use when we have a matched pair t calculation. So we do the difference in the D's and then divide it by SD, that's this 8.15 number here, divided by the square root of n. So we end up then with this critical value of 1.63. So this value here is a lot like our Z value when we do a Z calculation. So then we have to take this value, we got to take this value here and decide whether or not it is outside or inside of our critical value. So our critical value is, for this problem, 1.685 right there, which we get from looking on the chart, which I showed you how to do that. And so I know we covered that already. So we got our critical value there, and our value is just a little bit shy of that. So in this case here, we cannot reject our null. So I cut off the bottom here, so I'll put step 7 here. We compare our critical value to the value they, from the test statistic. And in this case, we cannot reject the null because 1.63 is actually less than 1.685. So we do not reject. Okay? So that is a, kind of a brief sort of how do we do this, what does this mean, sort of comparison, I think, which kind of then leads us into the next piece of this, which is moving into an ANOVA. So remember, with the t-test, we can only test the difference between two means. So in this case, we got our two groups here, right, our before and our after group. But now, what if we want to do more than one group? That's when we get into the ANOVA. So for ANOVA, we're going to compare multiple groups. So I wrote that on here. And in this problem here, this is problem 10.3. You can look at it in the textbook. It's not a problem. It's like a problem within the text where they, kind of show you how to work through a problem. And here we're looking at the amount of money that people spend on public transportation between Boston, New York, San Francisco, and Chicago. See my groups here, 1, 2, 3, 4. And ANOVA is an interesting tool that allows us to take a look at the variation inside of a group and the variation between groups. So we're going to look at the variation between, say, this group and that group, or this one and this one, 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 right? But we're also going to look at the variation within the groups, right? So within the group of Chicago, we're going to look at that. Within the group of San Francisco, within the group of New York, within the group of Boston. So when we compute our ANOVA, we're going to go down here. First thing, we set up our hypothesis, right? We're testing to see if group 1 is equal to group 2 is equal to group 3 or equal to group 4, or they're not equal. So notice how I don't have any mu's written here. I just say the groups are not equal because we don't know which groups won't be equal to one another. We're just going to hypothesize that something will suggest they're not different. So now the first thing we're going to do is calculate the group mean, and we're going to need the group mean to calculate our SSTR. So we get the group mean by taking, this is just x1 for Boston, x2 for New York, x3 for San Francisco, x4 for Chicago. We add them all up, we divide by 4, we get 1199. Now we use this 1199 number here to enable us to calculate our SSTR right here. So to calculate the SSTR, we want to, well, first of all, the SSTR is the sum of squares due to treatment. So in this case, we've got Boston, New York, San Francisco, and Chicago. We want to know if there is a difference between the groups. Okay, so this is telling us about these black arrows here. Okay, these black ones I wrote, the difference between groups. So the SSTR, we calculate by taking the n, so 5, because Boston had 5, and then we do 5 times the difference between Boston's mean and the average, and we square it. And then the next one we've got over here is the Boston, and this one is New York. We take the n and we multiply it by the difference between the actual and the average, and we square it. Very similar to how we calculate standard deviation once again. So we ultimately do all of that and we end up with this as our SSTR. And that means our sum of squares due to treatments is known to be 13,204,720. So from there we can calculate our MSTR, which is kind of what we're after here, because that's the numerator for our F test, because our ANOVA uses a F test. The previous one we just did was a T test, but now this is going to be an F test. So we calculate our SSTR by taking our 13 million number that we just calculated right here and dividing by C minus 1, where C is the number of treatments. C equals number of treatments. Okay, so now we have our MSTR and we know that it is this 4,401,000, etc. So we're happy about that, and we're going to take that number here and we're going to put it in our table. This is our ANOVA table right here. We're going to place it right there, and this is really going to be helpful for us to compute our critical value, because we're going to need that in our F computation over here. We're going to use it in just a minute, so we're going to leave that there for a second. We're going to move on to step 3. Here we're going to calculate the sum of squares error, which is the variation within the groups. Here's the formula for it right there, and the way we do it, we would take n minus 1 for the first group, multiply it by the variance of the first group, which is 87.79, and square it, and then we add n minus 1 times the variance of the second group, etc. And we get this 144,172. We then, just like before, we have to divide that by something to do with degrees of freedom, and in this problem here we divide it by what we call NT minus C, where NT is the number of treatments, but it's really the sum of all the n. So in our case it's going to be 5 plus 8 plus 6 plus 5, which happens to add up to 20, I believe, or 24 right there. So we take 24 and we subtract 4 from that, because that's C. We just determined that in the last one we did. And so we take 144,172 and we divide by 24 minus 4, or divide by 20, and we get this 7,209, and 7,209 gets then brought down. Well, first we take 144,172 and that goes down here. Then we have to do a couple things to both the SSTR and the SSE, and that is we divide by the degrees of freedom. So that's where we got the 4,401,000 here, and then here we're going to divide this 144,172 by n of t minus c. So that's going to give us 7,209. Now these two numbers here, we are really happy when we get these two numbers, because these two numbers provide us everything we need to calculate our F critical value. So we've got our numerator and our denominator here, so we can do our F, which is what we were doing all of this for, was because we needed to get this F computed. Because in ANOVA, the F tells us if there is a difference between the groups. So there we go. We got our 4 million number and we divide it by our 7,000 number and we get this F of 610. So essentially that tells us that our value is definitely different. There is a difference between our groups. So different, in fact, that we might say 610 standard deviations away from the mean, which is pretty darn far. So this, when we get a z value like that, we can just reject the null. We don't need to even look up on a t-table because, an F distribution table, because there's no way that's not going to be well beyond the critical value. So we're going to reject the null here because our F critical is significantly larger than our critical value, even though we didn't look up the critical value, but we could look up the critical value, and then I'll show you that we way exceeded. So let's just go ahead and take a quick look at the critical value. So you can see here I went ahead and just put a copy of the page so you can see it. When you look up an F critical value, you need the numerator degrees of freedom and the denominator degrees of freedom. So numerator degrees of freedom is always going to be C minus 1. Denominator NT minus C, which is the same as the previous page. So we end up looking at 3 right here in the numerator, and then 20 for the denominator. So our critical value then is 3.10. So 610, I believe was the number, is certainly greater than 3.10. Thus, we can reject the null. Indeed, differences do exist between the groups. We don't know where the difference exists, but we know there are differences. That's what this tells us. And then one last thing I want to just share with you is this. So I made up this table, and I'm going to post this also in my notes, but these are all exactly the same, so you just could have 3 of them. I just used them and cut them out and pasted them into my pieces of notebook paper. But you can see here where everything comes from and how you calculate everything. And I think this just lays it out really easily. I used this when I was taking this class when I was a graduate student, so I find this super easy to use, and it kind of explains where everything comes from. And I found this sort of missing in the textbook. So this kind of helps you get it all together. You're trying to get this critical value, that F over there, right here. That's what you're after, right? And that is computed by MSTR divided by MSE. I mean, that's what we're after. And we're going to compare that with our critical value right here. So, I'm very sorry about the technology tonight. Hopefully this helps. And I hope this clarifies things. And then I'll be posting the stuff for the next section here as well. So, all right, have a good night. Bye.